Hi friends, good evening. This is Deepak Dalvi here. I'm conducting your chemistry class 12 chapter for level 1. Its chapter name is Electrochemistry. So I'd like to introduce you with the contents of this chapter, uh, which are like electrochemistry consists of types of conductors and its measurements. So we'll be going through what is electrochemistry in the introduction, and then we'll be covering the types of conductors involved in electrochemistry and measurements involved in the conductors. Then also we will cover the conductivity, power of conducting the current in the conductive conductors, for which we need to understand what is equivalent conductivity and polar conductivity. And as a basic thing in electrochemistry is very important is electrolysis. Uh, I'll be covering that part also uh, as a mechanism of electrolysis, so that you know uh, next sessions in this electrochemistry will be uh, very well understood by you all. So let us go through each topic of this session, electrochemistry. So coming up with the introduction, see, actually, electrochemistry means what? Electrochemistry deals with electrical energy as well as chemical energy. That means in electrochemistry, energy is transformed from chemical to electrical energy or electrical energy to chemical energy. So, and the devices in which this changes happens, they are called as cells. So they can be electrolytic cell or electrochemical. So electrochemical cells means there is the chemical inside the cell, different type of chemicals, and the reaction in that chemical causes the electric energy to be delivered when they are connected in an electric circuit. And electrolytic is our main concern, which is a solution. In electrolytic cells, there is a solution. Either it can be in a molten form, or it is an electrolytic solution, which is an aqueous solution, or it is acid, base, or salt. So in electrolytic cells, reaction is non-spontaneous, as it is said mentioned here, and is how it is carried out. This non-spontaneous reaction, it is carried out by passing an electric current through the electrolytic solution. There are electrodes dipped in that electrolytic solution, which is called as anode and cathode, which will come in the later part of the section. So basically, through this electrolysis, high electropositive metals are produced, like sodium, potassium, calcium, magnesium, and also non-metals like chlorine, fluorine, and large compounds like sodium chloride, sodium carbonate, sodium bicarbonate are produced, which are the result of this chemical reaction that takes place in the electrolytic solution when an electric current is passed to the electrolytic. So here, what is happening in electrolytic cells? An electrical energy is converted into chemical energy, and vice versa. In electrochemical cell, it is happening vice versa. In this case, it is exactly reverse as compared to the electrolytics. So here, the chemical reaction is carried out between the chemicals inside the cells, okay, in an indirect manner, and an electricity is produced when this cell is connected in a circuitry. For example, we have our DC batteries, lithium batteries, and then alkaline batteries. So what is there? In these batteries, there is chemicals of different charge and positive and minus. So there are also positive and negative terminals for the cells. And when these are connected in electricity, there is a chemical reaction between the chemicals inside the cell. And due to this chemical reaction, the electric current is produced and it flows the circuit. So this is electrochemical reaction, in which chemical reaction is converted into electrical energy. And also there is an example of transmission of sensory signals through cells, and transmission of sensory signal through cells to brain, and also from brain to cell as a feedback. That is as a communication between the cells. Now all this is based on which principle? It is electrochemical principle. So this was what the type of it is electrolytic cell and electrolytic cells. Now what are the types of conductors? And we'll see what are the type of conductors uh, for use for electrolytic and electrochemical cells reactions. And further, we will understand the measurement involved in this conductor. Okay, so what are the types of conductors? So actually, first we'll understand the conductor, which is the conductor is a substance, right? It is a substance which allows the electric current to flow inside it when it is placed in the electric circuit. Okay, now conductor or a metal which does not, or a substance which does not allow the current flow inside it when it is placed in the electric circuit, that is called as insulator. Means insulator is a bad conductor of electricity and a good conductor is a good conductor of electricity current. So now conductors are basically of two types, which that is one is metallic conductor and other is electrolytic conductor. So electrolytic conductor in this, obviously, as the name suggests, metallic conductor means current flows when voltage applied across the ends of the terminals. So there is left side terminal, there is right side terminal as a conductor. When it is outside the circuitry, it is simple called as metallic conductor. But when it is placed in the electric circuit and one end of the conductor is made positive, other end is connected to the negative terminal of the circuit, then the current flows into it, then that is a metallic conductors. And there is no chemical change due to the passing of the current. That is a property of the metallic conductor. That's why it is called as metallic conductor. Now conductance of, and what happens to the conductance of the metallic conductor when the current passes through it, or when there is a rise in temperature. So as the current passes, there is a rise in temperature of the metallic conductor, and the residual positively charged ions due to this charging of the current in the metallic conductors. They are called as kernels. So what happens to these residual charges? They vibrate, and due to their vibration, they collide with the free electrons in the conductor. So their collision with the free electrons, there is a bonding, and because of this bonding, the resistance of the conductor increases. That is of the metallic conductor increases. And due to the resistance increase, what will happen? Obviously, the characteristics of the conductor to conduct the current will decrease. So this will decrease the conductance. Decrease the conductance means conduct means is to perform. Right? Decrease the conductance means it will decrease the current carrying capacity of that metal conductor when there is a rise in temperature. So now we discuss about the metallic conductor and its characteristics and properties when the current flows. Now what happens with the electrolytic conductor and what is electrolytic? Now electrolytic conductor are also known as electrolytes. Okay. And they are the substance which give positively and negatively charged ions called anions and cations. And they are available in the state of molten state of electrolyte or in an aqueous solution, an electrolyte. So electrolytes, what they have, it is a solution which can be an acid, base, or salt, okay, and it consists of ion. Okay, in which form? In either molten state or either aqueous solution. Okay, so and what happens when the current flows? Okay, when the current flows in such an electrolytic solution, the ions in the of the solutions, okay, ion in the electrolyte solution, which is they start dissociation, means ionization takes place. And what happens in this ionization? See, in electrolyte, as I had mentioned before, there are two electrodes, anode and cathode. Okay, anode is positively charged, cathode is negatively charged. So when there is ionization in the solution after when it is placed in an electric current, the positive ions which are in the ionization form in the ionization move towards cathode, that is negative charge, and negative ions move towards anode, which is positively charged. And since positively charged ion move towards the cathode, there is decomposition. And when negatively charged ion move towards anode, there is oxidation, okay, which is explained later also. And both the charged ions turn into neutralized particles at anode and cathode. Okay? And we get different uh, metals in molten form or and in gaseous or aqueous format. So this is what happens in this electrolytic conductor. Okay, when it is dipped in the electrolyte solution. So that is what is said in here, that these electrolytic conductors conduct current when ions in the electrolyte solution move due to application of potential PD. PD is what? PD is potential difference. Means voltage applied between the electrode, that is anode and cathode. Now what happens? Ions collected at cathode are called cations. They which undergo chemical decomposition and due to reduction of cations at cathode. Okay. And ions collected at anode are called as anions, and they undergo process of oxidation. Due to what? Due to their conducting current property. Again, now in electrolytic conductor, the conductors, as I said, in electrical conductor, the conductance increases. What happens in metallic conductor? The conductance decreases with the rising. But in electrolytic conductor, conductance increases with the rising. Why? Why? Because in ions, mobility is higher at higher temperature. Okay? So free electrons formation is more. So due to the rise in temperature in electrolytic conductor. So these free electrons, what is the characteristic of free electrons? Carrying a current. So so the conductance increases. Carrying current capacity increases means electric conductance of that solution. So that is the main characteristic of electrolytic conductor. Now, as I said, electrolytes are generally acids, base, and salts. Okay, that readily furnish ions. Substances that do not produce ions and are in molten states. There are some substances which do not produce ions and they are in molten state or in aqueous solution state and not in position to produce current, because they are not in condition to produce ions means they will obviously not dissociate, they will not have free electrons, and so they will not be ability to produce current when they are dipped in the solution, and even though they are charged with electrons. So such electrolyte conductors are called as non-electrolytes. Okay. and their example is like urea, sugar, etc. Okay. So we have that's what we have called a conductance, which is metallic conductor and electrolytic conductor, and the property of metallic conductor, property of electrolytic conductor. So next is we will understand as understood already regarding what is conductor. Now we'll understand what are the factors affecting electrolytic conductor. We will understand what are the factors affecting electrolytic conductor, which is very important to understand. So first is the what is the nature of the electrolyte? Whether so nature of the electrolyte means the extent of ionization. How much is the extent of ionization in an electrolyte? So the more the extent of ionization, more is the conductivity, okay, of the conductor. So the first factor is the nature of the electrolyte. The higher the conductor, as the conductor higher increases, the extent of ionization also increases. Means extent of ionization defines how much is the conductivity of the conductor. Second thing is factor is size of the ions. If the size of the ions is more uh, in the electrolytic conduction, then greater will be the solvation. Greater will solvation means obviously the conductance capacity will be less because the number of electrons free will be less as the size of ions is more. Again, the third factor is how is the nature of the solvent and its viscosity. Now, viscosity means what? The thickness of the solution. If the thickness of the solution it is less in flow, this is less viscous means the flow of the solution is uh, low. So, in less viscous, what will happen is conductance will be very weak. So, lesser the greater the viscosity, lesser the conductance. Okay, and viscosity less means flow will be good, so ion will be good, and so the conductance in that case will be high. So higher viscosity means thick solution, and lower viscosity means flow is good. Similarly, greater polarity of the electrolytic conduction will give the greater ionization. Greater the ionization means the conductance will be good. It is greater. Similarly, concentration of solution in an electrolytic conduction is also important. So if the concentration of solution is high, okay, that is molarity value or equivalent value of the solution is high, then the conductance is less. So solution concentration of the solution will be such that the conductance will be good. And temperature in an electrolytic conduction, the is directly proportional to the conductance. Okay, means higher the temperature, conductance will be good, or higher the it will be high. So these are the factors that are affecting the electrolytic conduction. Means affecting what? Affecting of the flow of current in a conductor when it is dipped in that particular electrolyte and charged to potential difference. What are the factors? It will be nature of the electrolyte, it will be the size of the ions produced and their solvation, then it is the nature of the solvent and its viscosity, and then concentration of solution and temperature. So, knowing about what are the types of conductors, what are the factors affecting the electrolytic conduction, what is the electrolyte, and what is the electrolytic solutions. Now we'll move to the measurements involved in the conductor. So, what are the major involved in a conductor? As you have studied, must have studied in 10th and 11th. Conductor or conductor conducts electricity. So, it has a resistance. So, measurements involved in conductors are resistance, then specific resistance or resistivity, then conductance or conductivity or specific conductance. So, these are the measurements involved in a conductor. Okay, now we'll understand these measurements. Okay, so as per Ohm's law, resistance is what? Resistance is directly proportional to length of the conductor, and resistance is inversely proportional to the area of the conductor. Okay, so what relationship we get between the resistance of the conductor and the length and area? That is, resistance is directly proportional to the length, and resistance is inversely proportional to the area. So finally, we get the equation like R is equal to rho L upon A. So rho is what? Here rho is called a specific resistance or is resistivity of the conductor. Now coming back, what do you mean by the resistance? See, resistance is opposite force. You can say in physics or a layman language. A conductor, when it is potential difference applied to the conductor, current flows. Now, if the resistance in the conductor is high, the current will flow slow or less current will. Means what? The force acting, electrical force acting in the against the direction of the current is high. That is called a resistance. Means that force is resisting the current to flow in the conductor. So that is called as resistance, and which is directly proportional to the length. Means what? Higher the length, longer the length, longer the distance, the resistance to the flow of current will be high. Lesser the distance, lesser the length of the conductor, then the resistance will be low. Okay, means current will be flowing will be easy or it will increase. Now, inversely proportional to area means what? If the area cross section of the conductor, okay, area of cross section of the conductor or cross sectional area of the conductor is more, then resistance is less. If the cross sectional area of the conductor is less, resistance is more. So this is the uh, characteristic. This is the dependency of the resistance on the area of the conductor. So when you remove the directly proportional symbol, you have to involve a constant in this equation. That constant is rho. Okay. And this is R is equal to rho L upon A. And rho is called as specific resistance or resistivity of the conductor. Now what it also has got the definition. So what is the definition of the specific resistance? You understand. So considering this length to be a single unit, that is centimeter, and area to be centimeter square, then resistivity is defined as the resistance of 1 cubic meter of conductor, that is one volume of the conductor. Okay, cubic meter means volume, full volume of the conductor. So, so resistivity is defined as a resistance. Means full conductor resistance is called as resistivity. That is, resistance of a 1 cubic meter of the conductor is called as resistivity. And is in that case, length is assumed to be 1 centimeter and area is 1 centimeter. So, and measuring unit of resistivity is what? Ohm centimeter. Okay. You can understand from this also. You can keep rho on one side. You can take A here and length down here. So, centimeter square divided by length will be centimeter and resistance unit is ohm. So, is ohm centimeter. Okay. Understanding resistance of conductor, let's understand the conductance of a conductor. So understand one thing: conductance of a conductor is exactly reciprocal of resistance. See, conductance, as its name suggests, ability to conduct, ability to allow, okay, so or perform, you can say. So it is exactly opposite to resistance. Resistance means avoid, stay away, okay, or prevent, okay, and conductance is allow, pass, okay. So exactly opposite or reverse of resistance. So conductors of a conductor, which is termed as G, okay, is exactly reciprocal of resistance of the conductor. So everything what is related to resistance becomes exactly reverse for the conductor. Okay, and as there is a specific resistance in resistance, there is specific conductor conductance in conductance, and there is also which is also called as specific conductance is also called as conductivity. Okay, or conductor. So having known that G is the inverse of resistance, that is 1 over R, specific conductance is what? It is exactly, again, it is reverse of specific resistivity, resistance. So it is 1 over rho. Okay, because and K is what? K is constant. When you remove directly proportional, you will get G is equal to K into 1 over R. So that is K is specific conductance or conductivity. Okay, and R is equal to rho L upon A. Okay, so G is equal to 1 over A rho into A over L. Okay, because exactly when you put 1 over R, at the place of R, you will get as rho L over A. Okay, putting in place of R rho L over A, you will get G is equal to 1 over rho into A over L. Okay, because L over A will go up here and A will be in the denominator. L will be in the denominator. So into A over L. Finally, what you will get G as? G is equal to K into A over L. Now what is K? It is 1 over rho, which is reverse of specific resistance or resistivity. Okay. And K is equal to what? Dot G dot 1 over A. Okay. 1 over A, it's L over A. Okay. If you put this value G is equal to K into A over L, from here itself, K will keep here, A goes here, and A goes down, L goes up. So specific conductance or conductivity is equal to G dot L over A. Now, the thing is, the SI unit of conductance, that is this G, is what? Siemens. Siemens or mho, it is called. And SI unit of conductivity is Siemens over 7 per meter. Okay, Siemens per meter in SI unit. And its CGS unit is Siemens per centimeter. Okay. Now, what is conductivity? Definition of the conductivity. We saw the formula of the. But definition of conductivity, it is a conductance of, just like resistivity is the resistance of 1 cubic meter of conductor. Conductivity is conductance of 1 cubic meter of conductor. Okay, and it helps what? Conductivity is the ability of a conductor to conduct the current. So it helps to compare the conducting power of solid conductors. Okay, conducting power of solid conductors. Higher the conductivity, higher the conductivity of a metal, higher is its conducting power, because conductivity is higher means ability to allow the flow of current is higher. So power is higher, conducting power is strong, it is higher. So Now, as Ohm's law is applicable to conductors, it is also applicable to the electrolytic conductor. Okay, is a conductor means here we are talking of metal conductor as a metal part. So it is also applicable to electrolytic conductor. Now, if you want to measure, when we come to the measurement, it's for the formulas of the conductors, being an electrolytic or a metallic. But now you have to measure it. Now measuring the resistance of a conductor, metallic conductor, in a Wheatstone bridge. Suppose now we have to measure the resistance of a conductor. We have to measure it in a Wheatstone bridge. Now measuring the resistance of conductor in a metallic conductor in a Wheatstone bridge is easy and it is done accurately. But same measuring of the resistance of an electrolyte, okay, or electrolytic solution, okay, it is having two problems. One is what the current is DC Western bridge normally. So that DC current changes the concentration of the solution which we don't want when we are measuring the resistance. Okay, concentrations will be stable. Okay, and secondly, the electrolytic solution, how we will have terminals, a liquid, how will it terminate it in the Western bridge? How we will assemble it in the Western bridge? That is the electrical circuit. Okay. So these are the two problems while measuring the resistance of an electrolytic circuit. How it is overcome? So these two problems are overcome. First is DC current issue is resolved by using AC current. Okay, means what happens in AC current? What we achieve by having AC current is a positive cycle in the AC current. Okay, charges and changes the concentration, but at the same time, negative cycle of the current again neutralizes that change. Okay, so there is no change in the concentration solution. That's why this is actually by using the AC current bridge. And now N terminals. How to produce N terminals to the electrolytic solution? Metallic conductor, it is not an issue. Electrolytic conductor, this is an issue. What we have done, what it is done, designed, a cell is designed that is dipped in this electrolytic solution. Okay. And then the positive terminal of that electrolytic cell, negative terminal of the electrolytic cell is assembled in the arm of the Wheatstone bridge. Wheatstone bridge has how many arms? Four arms. Okay. So one of the arm, that electrolytic cell dipped in the electrolytic solution and having positive and negative terminals is connected in the arm of the Wheatstone bridge. Okay. Now that design I can show you in a figure. This is the design of an electrolytic cell. See, now this is the electrolyte. That is a solution in the form of acid, base, or salt. And these are the metallic wires taken out of this solution. Okay, lead wires. Okay. Now, when the current is passed, then there is ionization happens in the electrolyte. So ionization happens in the plate. There should be something to collect those ions in the form of electrons, positive and negative. The design of plate is given. Okay, here it is a plate. It is platinized. The platinized coated plate it is. Okay, here at these two lead wires. Okay, now when one of these lead wire is connected to the negative of the Wheatstone bridge, that is negative potential difference of the Wheatstone bridge, and one is connected to the positive potential difference of the Wheatstone bridge. Now, since the figure is in front of us, I would like to tell you, which you will also come to know further also. Uh, Further also that the one electrode which is connected to the negative, it is called as cathode. The other which is connected to the positive is called as anode. Okay, and then the ion which flows towards anode are called anions. The ion which flows towards cathode are called cations, and cathode is negatively charged. Anode is positive. So this is one design. This is another design. There is an electrolyte in the beaker and another this thing cell, which is transparent cell or a glass cell, in which there are plates, platinum plates, and the wires. One is connected to positive, one is connected to negative. Positive for anode, negative. These are dipped in the electrolyte solution. It can be acidic and salt. And when this is connected in the Wheatstone bridge, which you can see in the next diagram, we can measure the resistance of this electrolytic conductor. And also, we can measure the conductor, which we will come to know further. So this is the Wheatstone bridge. Okay, the design which we have discussed in previous diagram. This is the arm in which that electrolytic cell is connected, and then that electrolytic cell it dip and can dip in an electrolyte solution later. So now, finding out the resistance of this conductance. Okay, now how it is measured? Now in the, how it is measured? Now see, if L is a distance between the two electrodes, the electrodes which are dipped in the electrolyte and then connected to Western pole. So if the L is the distance between the two electrodes and A is the cross-sectional area of one of the two identical electrodes, then we get the resistance that is equal to, we know the formula R is equal to rho L upon A. Okay, so from that resistance is calculated because here we know L and A and obviously the resistivity is resistance of the conductor. Okay, having 1 ohm resistance and 1 centimeter and area of cross section of 1 centimeter. So now from resistance we measure the value of conductance. How? Because conductance is exactly reverse of resistance. So G is equal to always 1 over R. Okay, and from the value of conductance, conductivity of the electrolytic conductor is because conductivity is again what? Conductivity of conductance of a conductor or specific conductance or conductivity of a conductor is G into L over A. Okay, L is a length and A is the area. Now here, now here this L over A is what? Which is very important. In case of conductance, J L over A, the L over A is called cell constant of the conductivity cell. Conductivity cell is the cell which we are designed as you see in the past figure. So this cell constant is very important measurement in the conductor, electrolytic conductor. Okay. So how is it important? That we'll see. Because once the cell constant of a conductivity cell is measured, it can be used to measure the resistance, conductance, and conductivity of any solution. Okay. Once the cell constants of a conductivity cell is measured, then we can find the resistance, we can find the conductivity, we can find the conductance of that solution because the electrolytes electrolytic cell is dipped in the solution and analysis takes place. And once we measure that conductivity, conductivity cell, constant of the conductivity cell, then we can measure the resistance, conductivity of this solution. But only knowing the conductivity will it solve our purpose? No, only knowing the conductivity will give what is the conductance, resistance, and conductivity of that solution. But how much strength, how much power the solution has to conduct the current. Okay, so power of various electrolyte solutions can't be compared. Okay, just measuring the conductivity, conductance, and resistance. Okay, power of various electrolyte solutions can't be measured because that power depends on nature, as you said in the factors of electrolyte. That depends on the nature and also depends on the concentration of it. Okay, so to know the power of various electrolyte solution, you know the nature of electrolyte and concentration of it. For this, to compare the conducting power of various electrolyte, we should know what equivalent conductivity or molar conductivity. So, which is the last the same part of this lecture session, measurement of in the conductance, which is the equivalent conductivity and molar conductivity. Why it is done? Why it is needed to measure? Know the power of various electrolyte solution. Okay. So what is this thing? As shown in the design of conductivity cell figure, it consists of two platinum electrodes. Okay. So what are those conductivity? It is equivalent conductivity and molar conductivity, which we know, which we need to know the power of the electrolyte. Okay. So equivalent conductivity, which is also mentioned as in previous section, defined as the conductance of a solution. Conductance of a solution containing 1 gram equivalent of an electrolyte. In case of equivalent conductivity, the it is defined as the conductance of a solution which has 1 gram equivalent of an electrolyte. Okay. So if volume, that is VML, that is 1 milliliter, VML, that is volume, milliliter is a volume of a solution containing 1 gram equivalent of an equivalent electrolyte, and K is the conductivity in Siemens per centimeter, then equivalent conductance, that is lambda EQ. Equivalent conductance of electrolyte symbolically represented as lambda EQ. So if volume ml, VML is the volume of the solution which is having 1 gram equivalent of the electrolyte, and K is the conductivity in Siemens per centimeter, then lambda EQ, that is equivalent conductance of the electrolyte, is equal to K into V. K into V. So where V is equal to 1000 over normal. Normality means it is equivalent of electrolyte. That is 1 gram concentration, 1 gram in terms of normality, 1 gram equivalent of an electrolyte. So K into 1000 over normality as per Siemens per cm square, and normality will be equivalent to 1 minus 1, because unit of normality is equivalent. So when it will go in numerator, it will be equivalent is to minus 1. Okay. And volume is termed as conductivity unit is SCM square. Okay. So SI unit, similarly, SI unit of equivalent conductivity will be S m square equivalent is to minus 1. Okay. So equivalent conductivity is depends upon the uh, conductivity of that electrolyte solution and the volume of the strain, that is into 1000 divided by normality. Similarly, molar conductivity. Molar conductivity is another fundamental property of the electrolyte. It is also frequently used. So, molar conductivity of electrolyte is defined as the conductance of the solution containing 1 mole of the electrolyte, containing concentration of 1 mole of the electrolyte, and it is related to the concentration, that is molar conductivity lambda m is equal to K into 1000 divided by molarity. Okay. So molarity is the mole of the mole concentration of the electrolytic solution. So unit of this lambda m, that is molar conductivity, will be again SCM square per mole, that is, or SCM square mole raised to minus 1. And its SI will be Siemens meter square mole raised to minus 4, or Siemens meter square per mole. Okay. Now, taking some examples to understand the power of the electrolyte solution, power of conductance electrolytic solution. So, to find out equivalent conductance molar conductance, we'll have some practice examples. And what effect does this measurement of molar and equivalent conductivity has is also we'll come to know from the practice examples. Okay. Saying that suppose the conductivity of a 0.25 m solution, 25 molar solution of potassium chloride KCl at 300 degree Kelvin, that is temperature 300 degree Kelvin, is 0.0275 Siemens per centimeter. Then calculate molar conductivity. Okay. Molar conductivity means lambda m. You have to calculate. So what is given here? Conductivity K is equal to 0.0275 Siemens per centimeter, and molarity is 0.25 m, that is mole. Okay, then find lambda m. So we have a straight equation. We have a straight equation of lambda m is equal to K into 1000 over molarity. So here we, if we put K is equal to 0.0275 into 1000 over molarity 0.25, we get the that is molarity of the conductor, that is 110 Siemens per centimeter square per mole. It is a not an SI unit. Okay? So this is what we get when we put in this standard formula. So what is the molarity of the conducting solution? Maybe it is 110 Siemens per centimeter square. Okay. Similarly, in second example, we have the resistance of conductivity cell containing 0.001 m mole, okay, of KCl solution at 298 degree Kelvin is what? 150 ohm. So resistance given is 150 ohm. Now here we have to find what? Here we have to find, they are told the cell constant. Okay. If the conductivity of 0.01 mole KCl solution is, here it is 0.0001, I have mentioned it by mistake. So 0.01 m KCl solution at 298 Kelvin is 0.146 into 10 to minus 3 Siemens per centimeter. What is given? Conductivity is given. Okay, so R is given 1500 ohm, molarity 0.001 is given, M and K is 0.146 into 10 to minus 3 cm per centimeters. That is conductivity. So how we will find out cell constant? Here we have to find it out indirectly. See, now this we will get in actual conductance. Direct relation of cell constant is with conductance. How? You'll see here. Now we know that R is given 1500 ohm. We need to find out conductance from R. So conductance is equal to 1 over G. Okay. Now when we put okay, when we put G is equal to 1 over R, we get G. Okay, and when we put G in that standard formula, K is equal to G into cell constant, which we have understood in previous section. So here directly we get directly we get cell constant is equal to K into R. K is equal to G into cell constant. Cell constant is what? L into L over A. We have seen in the last section. And K is found by 1 over R. Okay. So putting cell constant is equal to K is equal to G into cell constant. And cell constant will be what? K G is equal, as G is equal to 1 over R. So cell constant will be 1 over R into K is equal to 1 over R into cell constant. And we know the value of R. Okay. So cell constant will be what? K into R. So which is shown here. K is 0.146 into 1500 ohms. That is K is 0.146 into 10 raised to minus 3 into 1500, which will give you 0.219 per centimeter. Okay. This is cell constant unit. So once you find the cell constant, you can know other values also of the electrolytic solution of the conductor. Okay. So this gives you what are the measurements involved in the conductor as resistance, conductance, resistivity, conductance, conductivity. Then coming to the equivalent, okay, and molarity. All these are the measurements for the conductor. Okay, lambda eq and lambda n. Now, since we have touched the part of electrolyte solution and all, would like to explain a bit of what we mean by electrolyte. Almost we have covered in previous section, but with the diagram, I would like to explain you for your proper understanding. So this is the diagram for electrolysis, and it is a process of electrolysis is a process of decomposition of an electrolyte. Decomposition of electrolytes means ionization that takes place in the electrolytes, that is dissociation of ions when a current is passed in the electrolyte is called as decomposition. So process of decomposition of electrolyte by passing electricity, okay, to aqueous solution or molten state or fused state solution. So these are the two electrodes shown in the diagram dipped in the solution, dipped in the solution, which is electrolytic solution. So the electrode that is connected to the positive of the battery is called as anode, and electrode that is connected to the negative of the battery is called as cathode. So this is positively charged, this is negatively charged. And now there is the electrolytic solution, which is in the form of acid, base, or salt. Okay. So now when the electric current is passed in this solution, what happens? Negative, this ionization takes place in the solution. And ionization takes place in the solution means negative ions and positive ions are separate. When the so negative ions move towards anode, positive ions will move towards cathode. Okay, and in cathode there will be decomposition, and in anode there will be oxidation, and both the ions will turn into a neutral particle. Okay, so this is what the process is of electrolysis, and from this we get different types of metals in the molten forms, or in the gaseous form, or in the aqueous form. So this is what explained here of the electrolysis, and the important thing electrolysis, that is instrument used to bring about electrolysis is what called as electrolytic cell. Then it's in such cell, electrolyte is in the form of an aqueous solution or in the molten state. Two metal rods are dipped into it and are connected to a source of electricity. Now these rods are called electrodes. Okay, one is connected to positive, other is connected to negative. Positive is anode, negative is cathode. Okay, and oxidation takes place at anode. Okay, because the current charges over there, and reduction or decon takes place at cathode because there is no current flowing in there. So an electrolyte solution for electrolysis process can be what can be the solution type for electrolyte? It can be acid, base, or salt. Dissolve in water or taken in molten state. On reaching the respective electrode, ions lose their charge and become neutral particle species. Okay, means when the ions positive ion moves to cathode and negative ion to anode, they lose their charge and become neutral, like particles or species. Now, convergence of ions into neutral species at their respective electrode is called as primary change, and this primary change can be converted to the secondary change. Okay, in the later stage, in the later formation, the later reaction also. Okay, which comes the second part of the learning actually. So, having explained the electrolysis to certain extent, we can take the example to let you make understand it better way. What happens when an electric current flows and the electrolyte solution in which electrodes and cathode are dipped. So what happens? Now, for example, we are taking a molten lead bromide solution, the molten form. When the electrodes are dipped in such a molten lead bromide solution, what happens? So Pb, the equation we have is lead bromide, that is PbBr2, which is Pb plus 2 plus 2Br, and it is yes, donate the electron, it has accepted it. So 2Br, it is electron. Now at cathode, this Br being the negatively charged, it will move towards anode, and Pb being the positively charged, it will move towards cathode, which is negative. Anode is positive. So Pb ions, lead ion, will be moving to cathode, and they will lose their ion and will reduce into a molten form of lead, Pb. And at anode, bromine bromine will move, and it will give its one electron. Okay, and it will be in the oxidation form, which will be converted to Br. So oxidation will take place at anode, which is the Br2 is the result of that. Okay, and it will be in the gaseous. Now, so overall reaction will be what? Lead bromide will be converted to Pb at cathode and bromine in gaseous form at anode, and lead at cathode. So this is all about what we have understood in today's electrochemistry lecture for level 1. That is what is conductor and what are the measurements involved in the conductance and the electrolysis. Right? Okay. So hope you are qualified with this basics in electrochemistry and which can be developed further for your next coming up. Thank you and see you. Have a nice day.